Here we are going to look at an assembly example. We have several instructions, and we are going to see how we can convert that to machine code and eventually convert it to a binary number. So we have some data given to us. We have two arrays, or one array and one number on the memory. So that's a two label of X and Y. We do have the address of X and address of Y. So these are given to us. And that is actually here 0 missing. So here we have also the main label, and we have the address of the main given to us. We have total of 5 instructions. So you see there's 5. And some of these, as we have seen before, there are pseudo instructions, meaning that, for example, this load word might not be directly converted to a single machine code instruction. So one reason was that some of these, for example, we cannot fit it in 32 bits of data. So that's impossible. So that's why we have to basically break it into multiple instructions. Other example of, or other reason that we need pseudo instruction is some of these instructions are just there to help the programmer and make the life of the programmer easier. So for example, LA, or like having the label directly, or if you are doing a, for example, add I with a big number that is more than 16-bit. So those are some examples that you can do that, but actually they're gonna be broken into multiple instructions. Another example was LI that we just saw in the last slide, that it's actually using an OR. So that's examples of pseudo instructions. And if we have those, first we have to convert them, and then we can convert it to the machine language to get basically the hex value for that instruction. Okay, now let's look at how we can convert these instructions to machine language. So first one, we have load word, and we have seen before that load word cannot be directly converted because the label or the value of the label cannot be stored in one instruction, because that alone is 32 bits. So how that works, we have to use a different form of load word, which has basically, let's say, our register 23, and we are using some offset and then another register. So we are using basically this kind of format instead of the label. So how is that going to happen is to first construct that register using the load upper immediate. So part of this address, so this is what we want to load from. We are reading from the memory, the load word is reading from the memory, and it's reading from this address. So our final value that we'll have here, that offset on the register, is going to be this value. So how we do that? First, we are using a load upper immediate, and we are using register 1 that is basically reserved for the processor. So we are doing load upper immediate register 1, and we are using or building this top part only first. So we are putting here 1001 0000, and that basically is going to set register 1 to 1001. Sorry, Here we are just putting that one, and that is going to put that here. So that's our first step. So register 1 is that number. And then now we can use this second half, or the lower significant, as that offset value, because we have still 16-bit here on that format. So now we're going to have load word and register 23, because this is where we are going to load the data, and we are going to use this offset because that is going to get added to our register here, and we are going to register 1. So when load word is running, the processor gonna add this value and the content of register 1, which is that. So this is going to be 0010, and it's gonna be padded, sign padded. And of course, we're gonna get 1001, 0010, which is the same number as there. So that is basically for the first instruction. Now let's look at the LA here. So LA is basically a load address instruction. So it's going to look at the address of X, which is a label here, and it's just gonna load the address to the register 16. So here previously on the load word, we saw how we are loading the content of a label. Here in load address, it's basically a simpler version of load word in terms of if you are converting it. But again, LA is a pseudo instruction. We cannot have a 32-bit for the exact same reason. This is 32 bits, and we cannot store that whole 32-bit into one instruction. So we have to construct this address first. And basically for all the time that we are doing that, we are doing a load upper immediate, and we are just using register 1. So that's kind of like the basic thing. And first we do the upper half of that, or the more significant one, which is this. And it is a special case, by the way, I will show you. So that first, and then we're going to do an OR I with our destination, which is 16. And we are doing an OR between. So this is where the result gonna be stored, doing register 1 and the lower part, 0000. So this result of this is going to be basically this whole number stored in register 16. Exactly what load address is supposed to do. But also, we can simplify this. Instead of doing that, because here we are doing an OR with 0, it's actually unnecessary. So what we can do instead, we can do a load upper immediate and directly use this 16 and have that upper part, since the lower significant is all 0. So that is going to give us the same results. And that is for basically this second instruction. Now let's look at this save board. So that is your instruction. This loop is actually not directly translated. So what the save board is doing is, first the instruction itself is taking some value from your register 23 and storing it to the address that is being represented by register 16. So this is actually not a pseudo instruction. So there is no translation for that, or there is no extra step for that. We can directly look this up on the table and get some 6-bit for the opcode. And this is the I format. So we have another like 5-bit for the 2 registers and so on. So basically you get the same pattern as the table, and you can directly convert this one. So this is not a pseudo instruction. It's actually a basically like a machine code. Okay, let's look at the next one. Here we have add I. So add I, also this one is actually a basically a I format, and we can directly convert that. So we have 2 registers. So it's exactly the same as what we've seen in TF board. We have 2 registers and a 16-bit number. So if this wasn't 16-bit, so that's kind of the tricky. If this wasn't a 16-bit and it was actually 32-bit number, we could not use machine code for that directly. We should have do basically OR I and load upper immediate to construct that number and then do add. So that would be the case if this wasn't 16. So this was like 32-bit number. But since there is 16-bit, add I is actually with 16-bit is an I format instruction, and we can directly convert that. Okay. For branch less or equal, so this one we've seen that most of the branch are actually pseudo instruction, and they're being converted to different instructions. So let's look that up. There is BLE. It's actually, if you think about it a bit and like work on it, you can figure it out on your own instead of looking it up. It's very logical, but let's look at the translation. So we've seen this before, that there is the assembly language and there is the machine language. So BLE is doing a less or equal. So if register 13 is less or equal than register 17, this is 13 is less than 17, we are jumping to label. So what actually happens in machine code or machine language is that we are doing a set less than, but we are swapping the order. We are changing this order. Because if we want to negate this one, is going to be 13, and then this is greater than 17. So here, if we negate this, is going to be 13 is greater than 17, as you see here, because this is going to change. So, but what we are doing here, we have set less than, so that is our machine instruction or machine language code that we have. If you want to say or read this as a less than, how you are going to do this, you are looking at it from the other way. So you say, instead of saying 13 is greater than 17, you're saying 17 is less than 13. So is basically the first one is, so the sign is here, right? 17 is less than 13. So that's a negation of that original one. So we are saying if set less than, so if 17 is less than 13, register 1, so if this is true, if true, register 1 is becoming to 1. If it's false, register 1 is equal to 0. And then we are checking if these two are equal, we are jumping to label. So we are saying if register 1 is equal to 0, we are jumping. So you see that since this was negated, that means if this is false, so this was negation of the original thing that we had. Here, we would jump. If it's true, we would jump. Since this is negation, if it's false, we are going to jump. And if this is false, that means register 1 is equal to 0. So here we are checking if register 1 is equal to 0, then let's jump. So it's kind of like a chain of logical operations. And that's how we get from BLE to these two instructions. So we get to a set less than and a branch equal, but this is opposite. So if we go back, this last instruction is going to be basically that set less than and branch equal, as we just talked about it. It's a bit tricky, but it's doable. So this was 1 and then 12, and this is 16. And then here we have if 1 is equal to 0, we are jumping to loop. There is a $sign. But basically you can look from the table. And if you go to the next slide, we do have that logic here. So these are actually each step that we talked about. But the only thing here is that we have the main. So what was the address of main is 0040, 0020. So what is happening here is that the first instruction is going to that address. So you see here 400020. So it's same as this address. That's the first instruction. And then the next instruction is going to basically increments of 4. So from here, it's +4. The next one, again, +4. And so on. So that's basically your address space. And here you have your instructions that basically in each step, we done that. So far, we have our assembly code converted to machine code or machine language. So the last step is to actually convert each of these to their binary value. So if you look at here, we are seeing that, for example, load upper immediate is going to be this binary value. And I'm not going to convert each of these. We have done examples of this before, and it's exactly the same. You basically, all you do is to look up the table for this instruction or for each instruction, and you have to fill all the values in binary and basically continue like that. The only tricky one is going to be the branch not equal, because here you have a loop, and that's actually an address that we are jumping to. So that's our target. And here we have an I value. So this is the only tricky part here. And for that, we have to calculate the target address. So let's look at how that is done. So we did have our formula that is, let me just write it here. So we have this BTA is equal to program counter or PC, which is the current line of execution, or the current line, or the line that that branch instruction is located on. So that's the memory address of that line, +4, because we said we are always going to next instruction, and then plus we set some offset value. And then we said there is some relationship between offset and I. So this is offset and this is I. If you want to go from this offset value to I, so I is, so just to be clear, offset is the amount that we are jumping, and I is actually what we are putting on our on the memory. So here, like if I go back, so here, this value here, this is I. This is the 16-bit that we have. This is what we are actually saving in the instruction. Offset is actually the amount that we are adding to this formula to get to that target address. And we said the only difference is that if you go from I to the offset, you have to add 2 zeros here. If you are going from offset to I, you are removing 2 zeros, right? So because this offset is in bytes, but I is basically in lines of code, or how many lines of code you are jumping. So then let me write it here, offset. So offset to I, you are shifting to the right by 2. I to offset, you are shifting to the left by 2. So I is 16 bits, offset is 18 bits. And then, of course, here when you're using the formula, you have to do sign extend. Okay, so now let's fill the formula. So the target address is where we want to end up. So that's the final address that we have. And basically that's the address of the loop. So that's where we want to end up. PC is the address that the branch is located on. So if we look at back here, this is the branch instruction that we're actually converting, and this is the address that this instruction is located on. So that is going to be PC, and you see that we have that here, and then +4, and then plus offset. So from here, it's just a basic arithmetic. So we are basically moving this to the left, moving the 4 to the left. We are doing basically this subtraction. It is converted to addition. So it's like 2 complements, so all that. And we are getting this as the offset. So at this point, we have to look at here. We want from this offset, we want to get 1. Sorry, we want to get I, because we want to build this here. So all we have to do, we have to, well, I mean, you can be kind of smart about it, but like if you want to do it proper, you're going to basically convert this to binary. So you are getting all these numbers because f is 1 and then 0. And you're shifting your offset, which is this one, to the right by 2. So basically you are getting rid of this last 2. And you are taking 16 bits from that. So if I add here, so these are out, we get this 4, and the rest is 1s. So we get 1, 1, 0, 0, and then the rest is 1, and that's 16 bits. And you're going to see, if I clear this and going back, you're going to see that is what we have here. So that's your I value.